For example number 5, we're asked to find the intervals on which this function is concave up and concave down. We're also asked to make a rough sketch of the graph. So on the exam, you're going to have access to a calculator. Okay. Now I'm not sure if it'll be a graphing calculator or not, but we need to see some work justifying that your sketch is actually the right sketch. So you can't just plug this into your calculator and expect to get points for it. Okay. You need to be able to verify algebraically using some calculus that your graph is appropriate. So the couple things that we can do here is we can first find the derivative. Okay, so that's going to be 9x squared minus 8. So that leads us to our critical points. Now this is what I would want to see on a test. I don't want to just see the final graph. Okay. So the critical points for this are when this guy is equal to 0. So we have 9x squared is equal to 8. We're extracting the roots. So x squared is equal to 8/9. And of course we'll take the square root. So this tells me that x is both positive and negative. The square root of 8, which is 2 square roots of 2 over the square root of 9, which is 3. So we've now got two critical points. I'm going to call them x1, which is positive 2 square roots of 2 over 3, and we'll call the other one x2, which is negative 2 square roots of 2 over 3. So now let's go ahead and take these guys and plug them into the original function and figure out what their y values are so we can get some ordered pairs here. So I want one ordered pair, and then I want another ordered pair. So the original function is 3 times the x value, 2 square roots of 2 over 3 cubed minus 8 times 2 square roots of 2 over 3 plus 12. So this will give me 3 times 2 times 2 times 2 is 8 times another 2 is 16. So we're going to get 16 square roots of 2 over 27 minus 16. 8 times 2 is 16. 16 square roots of 2 over 3 plus 12. And so this will reduce to 16 square roots of 2 over 9 minus, now here's where we've got to be careful, okay? So this will be, I'm going to multiply top and bottom by 3, so 3 times 16 is 48 square roots of 2 over 9 plus, now let's get this guy over 9. 9 times 12 is 108. And we can always just go ahead and check that math. That's not bad. So 12 times 9, there's our 108. Okay, so we've got this. Again, I'm just doing this all in my head here. Okay, so what I've got is 16 minus 48. So I'm going to end up with 108 negative here. Okay, so that gives me 32 square roots of 2 all over 9. So that would be the ordered pair here. So that gives me 1. That's 2 square root of 2 over 3. And then 108 minus 32 square root of 2 over 9. Okay, and we do the same thing over here. So negative 2 square roots of 2 over 3. The only difference is that this guy changes to a plus. So we have 48 plus 16, which is 64. So we'll go 108. Okay, plus 64 square roots of 2 all over 9. Now, it wasn't necessary that we went through all this, but it gives us our ordered pairs. Now, what we want to do is we want to take those points and we want to look at the second derivative. So we know that these are candidates. 2 square roots of 2 over 3 and negative 2 square roots of 2 over 3 are candidates for critical points. So now what we want is the second derivative of that function. And so we have our first derivative up here, 9x squared minus 8. So the second derivative will just be 18x. So this implies that f double prime at these values, 2 square roots of 2 over 3, that's equal to 18 times 2 square roots of 2 over 3, which will end up being 18 divided by 3 is 6 times 2 is 12 square roots of 2. And we know that 12 square roots of 2, well, that's clearly a positive number. So since it's positive, that means our tangent function, our tangents are increasing, which means that this guy is a local minimum. And if we do f double prime at negative 2 square roots of 3 over 3, we'll get 18 times negative 2 square roots of 2, square root of 2 here, over 3. And so that will be negative 12 square roots of 2. And that's negative, right? So this tells us that this guy right here is a local maximum. So the overall graph, to sketch it out, okay, over here is negative 2 square roots of 2 over 3, and over here is positive 2 square roots of 2 over 3. Now, where do they fall, above or below the axis? It looks like they both do fall above the axis, okay? So I'm just going to put this guy right here, the negative guy, is actually a little bit higher than this guy right here, and that's going to make sense because this guy right here, the concavity, this, since it's a local max, this suggests that it's concave down, which suggests that the function looks like this. Over here, since a local min, suggests concave up, like this. And so if we connect them like this, we get our function. Now this isn't a real good drawing, so I'm gonna go ahead and make it a little bit more smooth in between there, or do my best. Okay, so we think it looks something like that. Now, if you go back up here, those were the only two critical points that we had, and so we ended up with this situation right here. Okay, now one of the things to note is that in between it looks like there was a change in concavity. Well, the question is, when does the change in concavity occur? Well, f double prime of x was equal to 18x. A change in concavity is when this guy is set equal to 0. So f double prime of x equals 0 that leads to a change in concavity. So f double prime of x, or at least it's a possibility for a change in concavity. So that is when x is equal to 0. So 18x equals 0, so x is equal to 0. So at 0, right here, we've got a change from going concave down to concave up.